So my function was minus 3x plus 5 plus 3 over x plus 1. So first of all, I turned it into a usable format by using the lowest common denominator, x minus 1. So I got minus 3x squared minus 8x plus 2 all over x minus 1. So first step is to state the restrictions, which is x cannot equal 1, because if it did, the denominator would equal 0 and the whole function would just not work. So after finding restrictions, we have to state the vertical asymptote, which is x equals 1, which you can see in the graph right here. X equals 1 is the vertical asymptote. And then step number 3, or the next step, is to choose two numbers that are really close to your vertical asymptote and find if the function is above the x-axis or below. So after plugging in really close numbers to x equals 1, you get, as x is approaching 1 from the right side, y is going to positive infinity, and x is approaching 1 from the left side, y is approaching negative infinity. As you can see in the graph here, on the right side, our function is approaching positive infinity, and on the left side, it's approaching negative infinity. The next step is to find if we have a horizontal asymptote or a linear oblique asymptote. In our case, we have a linear oblique asymptote because the numerator degree is greater than the denominator degree. So to find the lowest or the linear oblique asymptote, we have to use the numerator divided by the denominator. So after we solve for that, we get minus 3x plus 5 as our linear oblique asymptote. We don't worry about the denominator because it's irrelevant. So here our linear oblique asymptote is y equals 3x plus 5, or negative 3x plus 5. And then you have to use really big numbers to find if the graph is above or below the lowest, or not the lowest, the linear oblique asymptote. So first, we're going to sub in 1000 into our LOA, which gives us a negative value, and negative 1000, which gives us this number. And then we have to check the same thing, using the same two numbers, which is 1000 and minus 1000, and sub it into our f of x function over here. So after doing that, we find out that as x is approaching infinity, your f of x is less than the LOA. The same thing goes for when x is approaching negative infinity, your f of x is lower, or is less than your LOA as well. Okay, so our next step is to find nice points, which is the x-intercepts and the y-intercepts. So in our case, our x-intercept, you have to solve for 0 for the numerator, or make y equals 0 for the numerator. First, what I did is checked if I had any real roots or not. So I used the discriminant, b squared minus 4ac, which I got a positive number. That means two roots are real. So I subbed in these three numbers into the quadratic equation, and then or the quadratic formula, and got x equals 0.279 and x equals 2.387 as my two x values, which you can see on the graph here, 0.279 and 0.387. And then we solve for the y-intercept, which you just sub x equals 0 into your f of x, and you get, which I got 2, so my y-intercept is 2, which I also labeled on my graph, which is 0, 2. And then the next step is to find if your graph has any points of intersections where it crosses the LOA. So for that, you have to make your f of x equal LOA, and then once you solve, you get minus 2 equals minus 5, which can't happen because it doesn't. So therefore, there's no POI, or point of intersection. So therefore, my graph looks like this. And thank you for watching.